In order to be able to look at problems to do with magnetic fields and charged particles, we need to be able to draw things in 3D. So I'll just go over for you our convention for drawing magnetic field lines. So the magnetic field around magnets is very similar in shape to the patterns of electric fields around charges. So the shapes you're going to see look very familiar. Just like electric fields, they're three-dimensional, and because the situations are often 3D, we need a way to show it. So things in the plane of the page are easy, but to be able to draw magnetic field lines in and out of the page, we're using the convention that a field coming out of the page is shown as dots, while a field into the page is shown as crosses. Think of a dart coming towards you. You'd see its sharp tip as a dot, but if it was moving away from you, you would see the feathered tail of the dart showing as a cross. So moving charges create magnetic fields, and we can work out the direction of the field lines created by a current using the right-hand grip rule. Now there are lots of variations of right-hand rules. I'll show you the ones I know, but you may have already seen some in textbooks or used by other people that are different. So as long as your system works for you, it's fine. Now the first way I use the right-hand grip rule is to work out the field around a straight wire. Point your thumb in the direction the current is flowing, and of course that's conventional current. Then your fingers that are curling around point in the direction of the field lines. Note that the current and the magnetic field are at right angles, so that the current is vertical and the magnetic field is going in a circle in a horizontal plane. The second way you can use the right-hand grip rule is if the current goes in a circular loop. You can still use your thumb to represent current and your fingers show the magnetic field. However, it still works if you curl your fingers in the direction of the current and then just remember that your thumb is pointing to the North Pole. A solenoid, which just means a coil of wire, is just a lot of single loops next to each other. Their magnetic fields add up, which means we still use the same rule as we did for a single loop to work out the direction of the field lines. You can see that the magnetic field surrounding a solenoid is the same shape as the field around a bar magnet. Again, you use the right-hand rule, and if your fingers go in the direction of the current, then your thumb is pointing to the North Pole. So now to define the strength of a magnetic field. The first thing we need to know is the equation for the force that a magnetic field exerts on a charged particle that is moving. The force Fb equals Q, the charge, times V, the speed, times the field strength, which is capital B. By comparison, the force on a charge due to an electric field was just the charge times the field strength. There was no term there to include the movement of the charge. Now, if V and B are not perpendicular, then we have to add a sine theta term. So now we have F equals the magnitude of the charge times the magnitude of the speed times the magnitude of the field times sine theta. That equation then gives us a definition for magnetic field strength. Where the electric field strength E was defined as the force per unit of charge, B is defined as the force per unit of charge per unit of velocity. The direction is something we'll need another right-hand rule to work out. But first, units. We measure B in Tesla, and like coulombs and farads, it's a large unit. The current record for the strongest magnetic field ever produced is about 90 Tesla. And by comparison, Earth's magnetic field is about 5 by 10 to the minus 5 Tesla. So when it comes to the magnitude of the magnetic force, the equation tells us that the force is strongest when the charge is moving at right angles to the magnetic field lines, and it actually is zero if a charge is moving in the same direction as the field. To work out the direction, we use the second right-hand rule, sometimes called the right-hand push rule. So the force, the direction of movement of positive charge, and the magnetic field are all at right angles. So if your thumb points in the direction a positive charge moves, which also means the direction of conventional current in a wire, your fingers point in the direction of the magnetic field, and your palm pushes in the direction that the force acts. Let's do a quick example. I want you to work out what is the force, and that means size and direction of it, on a proton travelling at 1 × 10⁶ meters per second to the right in a uniform field of 0.35 Tesla, directed, as you can see because it's crosses, into the page.